Matrix Encryption, the most powerful encryption in the world. What is Matrix Encryption? First and foremost, Matrix Encryption is a patented piece of cryptographic technology having United States Utility Patent Number 11777714. This is no mere design patent. The patent was issued on October 3, 2023, and has an active status, with all the patent protections afforded by law. The inventor is listed as Watson Knox Williams Jr., having filed as an individual, and you may read about the invention and download it at your leisure. In addition to owning the Matrix Encryption patent, Watson Williams is the owner of 777 Technologies, a startup software company built to develop Matrix Encryption into cryptographic products and services for purchase. Alright, so what are we talking about here? The most powerful encryption in the world? Who does this guy think he is? Well, the summary is that Matrix Encryption has achieved fully scaled, combinatorial, rational-based, non-algebraic functional block encryption with post-quantum resilience. To understand how matrix encryption might be stronger, we need to talk about the current standards in encryption technology. Two relatively well-known forms of encryption are AES and RSA. AES, or Advanced Encryption Standard, is a symmetric block cipher algorithm used to encrypt and decrypt data using a single key. It was established by the United States National Institute of Standards and Technology in 2001 and uses a sequence of byte-level transformations to protect data that can be performed over and over again in rounds. The Advanced Encryption Standard is widely used across the globe to secure data. It has been adopted by government agencies, emergency response teams, and private companies due to its robustness, efficiency, and speed in processing large volumes of data. AES has become the federal standard for encrypting sensitive information. It is used in various applications, including securing transmission across the internet, encrypting files and databases, and safeguarding sensitive communications in wireless networks. RSA is a public key crypto system, also known as asymmetric cryptography, which uses a pair of keys, a public key for encryption and a private key for decryption. The public key can be shared with anyone, while the private key must be kept secret by the receiver. RSA was developed by Ron Rivest, Adi Shamir, and Leonard Edelman, who published the algorithm in 1977. The security of RSA relies on the difficulty of factoring large numbers into their prime factors. RSA is widely used in various fields for secure data transmission and digital signatures. It is extensively used in online banking, e-commerce, secure communications, and email encryption. Additionally, RSA is used in software programs like browsers to establish secure connections over the internet and to validate digital signatures. Resilience and brute force. In cryptography, resilience refers to the ability of cryptographic systems to withstand and recover from attacks. Such attacks may attempt to exploit the internal structure of the algorithm. However, with sufficient resistance, the only recourse becomes a brute force attack, where all possible keys may need to be tried in order to break the encryption. The caveat here being that with RSA, half the key is already given, and we don't need to try any other keys. The problem is simply a great computational difficulty of factoring out the answer, or the private key. For symmetric key cryptography, resilience to brute force can be thought of as the relative number of possible keys that may unlock the encrypted data. And so for AES, the number of keys, or the key space, is on the order of 10 raised to the 77th power. It would take a supercomputer capable of trying a billion keys every second around 10 to the 60 years to break. That's about a trillion years. Yikes. That's unimaginably large. However, there is something called Grover's algorithm that reduces the number of keys that need to be tried by the square root of n, which is impressive, but still leaves breaking AES beyond reach for any foreseeable quantum system. An interesting thing to note here is that recalling the byte level shifting and mixing of data of AES that occurs round after round, this process only indirectly increases resilience, but does not increase the size of the key space, and simply makes it so that a so-called structure attack is next to impossible. As far as RSA is concerned, as we alluded to earlier, half the answer is already given. The only protection is that the answer would take too long for a computer to factor. But with the advent of quantum computing and another process called Shor's algorithm that can factor much faster than the norm in something called polynomial time, a large enough quantum computer could theoretically break RSA 2048 in hours. This is why RSA is not considered quantum resistant, and it's my opinion that the asymmetric key philosophy, at least with respect to RSA, of being able to securely give half the key away simply based on a computational wall may be fundamentally flawed, or at least not the optimal approach. RSA is novel, but is being phased out by Apple, Google, IBM, and others, and is set to be replaced by some new, custom-designed, quantum-resistant architectures by 2035, according to sources. The thing I like about asymmetric cryptography, at least in principle, is that it works with math, which is where I see the heart of cryptography. Whereas modern symmetric key systems focus on byte manipulation, they don't try to handle numbers themselves directly, but settle for swapping the data given around over and over again. And to me as a researcher, there's something lamentable about that. I dare say the cryptography community has become enamored by the computer language itself and appears to have all but abandoned number theory for a fixation with byte-wise musical chairs. So what do I mean exactly? Well, we have to understand that there are certain data types in terms of how data is processed, and most relevant here are integers, or ints as they're called, floats that refer to decimals or fractions, otherwise known as rational numbers, and strings that define text or language data that may include numbers. Even though symmetric cryptography is done using numbers, namely ones and zeros, the data type is still a string and is often referred to as a byte string. This will hopefully be a review for some, but each 1 and 0 in a computer represents a single unit or bit of data. There are 8 bits in one byte string, and there are 256 possible 8-bit byte strings. This is related to the resilience of AES, although technically AES keys are binary strings up to 256 characters in length, rather than being mapped over all 256 possible byte strings, like RC4, which has a resilience of 256 factorial. Floating point decimal rounding error and the exclusion of floats. So we have seen that asymmetric cryptography, like RSA, there's also elliptic curve cryptography that we didn't talk about, and others, operate with math and numbers, but there are some numbers that are just not compatible with the binary language of computers. In particular, some floats are not convertible to and from binary because their binary expansion is infinitely long and must be rounded or cut off. For this reason, any operations that may cause the sort of rounding error to occur are ignored and do not appear to play a significant role in modern symmetric key frameworks. Donald Knuth, who wrote The Art of Precision, is quoted as having said that floating point is a leaky abstraction. But if any one figure played the most pivotal role in the development of this issue, perhaps it would be Claude Shannon, the father of information theory, who redefined the foundations of data and communication in binary, discrete terms, establishing an enduring paradigm that excluded floating point representation from the heart of secure computing. So, just so we're crystal clear, fractions or rational values are generally avoided in terms of data security. Now that we've been introduced to the current state of the art, how does matrix encryption measure up? In the beginning, there was CBD. The original CBD function, before any thought of an encryption application, was designed to count decimals or rational numbers recursively in batches to infinity. And not just any rational numbers, but only Q* rationals. That is to say, only those rational numbers between 0 and 1 whose decimal expansions are finitely long. This naturally excludes values like 1/3 from the domain, however leaves all real values inside the interval that have infinite decimal expansions like 1/3, 1/7, 1/9, pi-3, etc., as domain limit values that can always be approximated to any desired accuracy with elements within the domain. The CBD graph, which we call the Geyser graph for its shape, is the only graph I know that recursively and discretely grows vertically to infinity within a fixed domain, and yet never violates the vertical line test of functionality. This is essentially a bijection over the specified domain, which is important in terms of cryptographic potential. The growth of CBD from batch to batch is so rapid, the general shape of the graph is best depicted with a log scale on the y-axis. After I found the original CBD function, I could only wonder about an inverse, as the nature of the length and ceiling functions within made algebraic derivation impossible. Months would go by until one day I woke up from a dream with the idea to try reversing the signs and to use the floor function, even though I knew it wasn't the algebraic inverse, but only the logical inverse. Lo and behold, it worked. I found the non-algebraic inverse function inductively. So here the core functions of matrix encryption are displayed in their modified, reduced forms. Modified meaning that the original domain, and consequently the form of the functions, has been modified from Q* rationals to the natural numbers so as to bypass rounding error, because remember, even finitely long decimals in base 10 can be infinitely long in binary and in such cases would be rounded off, resulting in data loss. And reduced in that algebraic substitution has been performed on them, absorbing the secondary functions seen on the previous slide. And suffice it to say, even though we have shifted the domain to the natural numbers, I'm afraid those fractions, particularly the term over 9, is going to cause a big rounding error problem for our hopes of ever using CBD cryptographically, unless we're able to find a solution. Finally, though the respective domain and range elements appear to be close together, only 2 apart, this phase shift, if you will, is cyclical across each batch, and the cycle explodes, becoming longer, more vast, and non-obvious towards the middle of each batch of integers for larger and larger batches. The key implementation in matrix encryption involves encoding the data with a variable codex, which we'll take a closer look at later, into a concatenated or combined integer that is then literally added to an integer key of the same length, producing the keyed encoded data ready for the forward function. There are plenty more caveats here, but let's just keep things as simple as possible. This key implementation eliminates structure and regularity from the deterministic core functions because without knowledge of the key, you will simply map back to the wrong domain element. So the top-down view of what matrix encryption does is that each character in plain text or each byte in a file is consecutively assigned a numeric value out of a field or matrix, if you will, of possible values. This converts the raw data into an integer data type rather than decomposing into bytes. We add the key and run the forward function producing the encrypted data. In reverse, we begin with the encrypted data, subtract the correct key out precisely as previously shown, producing the unlocked encrypted data that becomes the correct integer input that must then be used for the inverse function. But then during decoding of the output, that is the encoded data, we will only recover the original data if we used the correct character map or codex. So the use of a codex and a key in tandem creates a powerful level of defense, as we'll soon see. Let me get this straight. You're saying that matrix encryption uses a combination of data types, including rational values, and is somehow immune to rounding error, contrary to what the prevailing wisdom in the field teaches about avoiding rational numbers. So, how is this possible? Sometimes, if you believe in something enough and you won't take no for an answer, a way is revealed showing how it could be so. In the pre-patent developmental phase of matrix encryption, I had reached a wall. The algorithm didn't seem scalable because dividing by 9 was causing rounding error after just a few characters of text. Sometimes I'd see scientific notation that completely failed to express the data. I didn't know what to do. I thought to myself, maybe you should quit. This cryptography stuff isn't for you. You don't know what you're doing. You never went to school for data science. But I refused to give up. I just knew deep down there was an answer. And in a sudden flash of insight, I saw numbers adding up and approaching the solution, and so I got to work. The first term we call the trimmed sum of n, and the second term expresses the more familiar so-called digit sum, or the sum of digits of n over 9. This technique greatly limits the potential for rounding error as only the sum of digits is divided by 9. And as we'll see shortly, this technique would ultimately prove to be sufficient to totally eliminate rounding error altogether. In general, the resilience of matrix encryption is given as the reciprocal of the multiple of the key space and the codex space. In order to know what that looks like, we will have to consider each separately, then combine the solutions for a proper perspective. All right, you're in for a treat now because I was going to give the short version of the codex resilience, but let's actually take a little closer look because I've come to realize that optimized codex handling is really the final frontier of matrix encryption to minimize and ideally eliminate any discernible structure in the global matrix encryption algorithm. First of all, matrix encryption assigns each unique character in the case of plain text and each unique byte in the case of files to unique integer values. This means any repeated characters or bytes receive the same integer value. There are 94 characters on the standard keyboard. The original plaintext codex called for 81 numeric assignments because this is the number of two-digit integers that don't end in 0. Such two-digit integers ending in 0 were classically avoided in order to prevent data loss of the very last character of text in the event they appeared as a result of the last character's assignment from the codex. Not a big deal, but important and relating to injectivity for edge cases of the CBD counting procedure. So the original plaintext codex resilience is P of 94 pic 81, which is approximately 1.75 times 10 to the 136 power, which is already much greater than the AES key space. As matrix encryption has evolved, I've come to see that the excluded values ending in 0 are theoretically salvageable, and that maximizing the number of codex assignments will make matrix encryption even stronger. Now, in actuality, there are 100 possible two-digit combinations that could be assigned in a two-digit codex, running from 00 up to 99. And ideally, the codex should have 100 assignments, not just 81 or even 90, but for one thing, there are only 94 characters on the standard keyboard, so there will necessarily be a slight gap between the digital assignments that are getting filled by a given custom codex and the theoretical assignments that could be filled if there were more standard characters to work with. And we can't just use a few non-standard characters to fill the gap because they tend to be larger than a single byte in size. Another issue here is that 00 through 09 are problematic as integers with the leading zeros if they appear at the beginning of an encoding, and for the fixed length integer scheme, if the leading 0 were to be removed, it could corrupt the data during decryption. And we currently have this in R&D. Nevertheless, the original plaintext codex is quite vast, and our 256 file encryption does not have this structural disadvantage at all, as no gap, in other words, as like RC4 briefly mentioned earlier, we map all possible 256 byte strings. There are no gaps out of base 256, only we're mapping them from an even larger space of around 8 or 900 three-digit integers, so the file codex resilience of matrix encryption is around P of 900 pic 256, which alone is breathtaking. Furthermore, it should be noted that there's nothing stopping us from doing three-digit plaintext assignments, or even greater. These numbers may seem big, but you haven't seen anything yet. Let's briefly touch on padding in matrix encryption. What we mean by padding is different from the traditional symmetric key definition of padding, which is necessarily done to standardize the length of data to a multiple of the block size, usually 8 or 16 bytes for AES. In matrix encryption, this is not necessary because the key is always required to conform exactly to the length of the encoded data. And so we will define padding in matrix encryption as voluntarily putting an arbitrary amount of junk characters before, after, and sometimes among relevant data at will. With gibberish padding behind a relevant message, it will not matter if the last character comes back as a % rather than a 7, for instance. Using padding is essentially all we have to do to operate competently with Codex 90. Now, I know that was a lot of information to take in relating to the Codex implementation, but it will actually make the last part of this presentation easier. As far as the key resilience goes, because remember, we're still trying to calculate the true resilience of matrix encryption, it's a little easier to understand. And the key resilience is related to the number of integers with a given number of digits. For instance, there are 9 one-digit integers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 90 two-digit integers, 900 three-digit integers, etc. You get the point. And the function 9 times 10 to the length of n minus 1 will always give us this value. The number of possible keys in matrix encryption then is given by 9 times 10 raised to the 2 times the length of n minus 2. As is clear, the key space grows exponentially. The variable is in the exponent. And since the number of possible keys is functional and dependent on the length of raw data, larger amounts of data will always find greater degrees of resilience under encryption. Let that sink in. Longer messages are always more secure, not just for a step or two up to a larger key, but continuously. And it is this variable key space that dominates the true resilience calculation, regardless of the size of the codex space used. Now behold the true resilience of matrix encryption. As a function of the codex space and the key space multiplied, a chance of 1 in 81 factorial times 9 times 10 raised to the 2 times the length of n minus 2. Note that we're using a low-end codex estimate of 81 factorial for simplicity, but isn't she beautiful? For example, if we have a 1,000-character message, the length of n is 1,000. This means there are 9 times 10 to the 1,998 possible keys. But then the codex adds well over 100 significant digits to the exponent, and so we can safely say that if the message is 1,000 characters, honestly a modest message length, the resilience will top 10 to the 2,000th power. Likewise, if n is 10,000, the resilience will be over 10 raised to the 20,000th power. Are you beginning to see a difference in caliber? Could matrix encryption be the post-quantum computing technology the world has been anticipating? For no known algorithm approaches this kind of power. Recursion of the floating identity and theoretically limitless information fidelity. As we revisit the floating identity, which rescues rationals of the form n over 9 from the jaws of unusability, let us understand something even more profound, that through recursion it becomes possible to totally eliminate and otherwise vanquish the possibility of rounding error. If we let the first expression be represented as the trimmed sum of n, or the TS of n for short, and the second expression in the numerator be written as the digit sum of n, or the ds of n, then also noting that the ds of n is ultimately an integer value itself, which allows us to rewrite ds of n as the next variable o. From here, it becomes clear that O over 9 is identical to n over 9 in form and can also be expressed with a nested floating identity. Hence, n over 9 is equal to the trimmed sum of n plus the trimmed sum of O, which is the same thing as the trimmed sum of the digit sum of n, plus the digit sum of O, or the digit sum of the digit sum of n, over 9. To fully generalize this logic, we can recursively take the digit sum all the way down to what is known as the digital root of n, which will have only a single digit. To do this, we simply let the ds of O be equal to a new integer value p. Then let ds of p equal q, and let the ds of q equal r, etc., all the way down to the ds of y producing z, the digital root of n. This allows us to declare that n over 9 for all positive integers is equal to the trimmed sum of n plus the trimmed sum of O, or the trimmed sum of the digit sum of n, plus the trimmed sum of p, which means the trimmed sum of the digit sum of n, etc., down to the final trimmed sum producing the digital root of n over 9. And this value will always be between 1 and 9. If z is 9, then the last term will be 1, because 9 over 9, of course, which means that n is evenly divisible by 9. Any other value indicates non-divisibility by 9. But again, it doesn't matter because the entire whole part can be extracted in this manner. And referring back to the inverse CBD function, that remainder is rounded down by the for function anyway, so it isn't even used or needed. You may have heard before that if the sum of digits, or technically rather the digital root of a number, is equal to 9, then that number is divisible by 9, and that this only works with 9. Recursion of the floating identity is related to this fact, but captures a more in-depth and utilitarian representation. To fully appreciate our final section, we need to return to AES and RSA for a moment and ask the question, what happens when a wrong key is used?
You must unlearn what you have learned.
Inasmuch as we must admit that encryption is not something typically thought about or understood by the average man, much less should we expect them to be likely to conceptualize on their own one of the greatest weaknesses of current binary-based symmetric key systems. And so let us illuminate that little-known weakness for a collective understanding. The binary architecture of AES is such that when we use a wrong key, the decryption usually fails immediately on a padding violation. Remember, we talked about padding being necessary in AES. And I have personally witnessed this using a free AES web resource and found that indeed, with the wrong key, you get no answer at all but an error. While I don't have first-hand experience with RSA and key violations, it is my understanding that a wrong key may return an unreadable blob of data or error during modular exponentiation. The problem is that such errors prevent any benefit from a situation where, simply based on the key used, it is not possible to know whether the decrypted data is correct or not. I will say that one impressive thing about the traditional binary key system is that just being one digit off in the key will seem just as wrong as any other random key, and both will equally result in error and no data. So in this regard, almost having the key is essentially as useless as being totally off from the actual key value, but again, the trade-off here is that wrong keys are obviously wrong and can therefore easily be discarded, making attacks more efficient. The faux decryption principle in matrix encryption a game-theoretic layer of protection. Matrix encryption represents a paradigm shift in cryptography because the algorithm has the property of false positive resilience. This means that wrong keys must be discarded not via a simple error, but via a decision of no, this output seems wrong, or yes, this output seems right. In most cases, the wrong key will produce alphanumeric gibberish, but even this cannot necessarily be discarded based on unreadability, because it is possible to layer matrix encryption with AES, for example, taking an alphanumeric AES encryption as the raw input for matrix encryption. With a wrong key, occasionally there will appear coherent faux messages that will seem plausible, but which will ultimately lead nowhere. This gives the term plausible deniability meaning to the world of data science. Matrix encryption requires us to talk about a new type of resilience, not just brute force resilience, not even structural resilience, but false positive resilience. So let us define false positive resilience as the probability that for a randomly chosen key codex combo, the output yields syntactically or semantically valid looking data, such that no oracle or external validation can reliably distinguish a fake from the true data. So this will be a percentage of plausible key codex combos out of the total key codex combo space. In order to formalize and to quantify the FPR, we will need to define plausible decryptions, and we will say that plausible decryptions are all those decryptions conducted with any key codex combo whatsoever that result in data with a length of 1/2 the length of the encryption, in the case of 2-digit codex assignments. That's all. And without getting explicit, we can conceive that if even 1 in a million wrong key codex combos produces data of the correct length, there will exist literally countless trillions and septillions and googals of plausible decryptions to parse through logically. Not just algorithmically, these require a decision, and this is simply not possible for any foreseeable quantum system. And in the case where the codex is idealized with no assignment gaps, as with our file encryption, every single key codex combo will produce a false positive or plausibly correct message. So the FPR will be 100%, as decryptions that are too short are only produced by gaps in the combination matrix. And the point here isn't that wrongly decrypted files will seem like reasonable file data, but that nothing about an encryption, not even the length, necessarily indicates what has been encrypted in the first place. Let's think about it by way of analogy. In the classical system, you try a wrong key and the vault explodes in your face. That was the wrong key. But in matrix encryption, the new paradigm, you try a wrong key and the vault opens into a perfectly decorated fake room. You're lost in a mirror maze with no way out in sight. We believe that misdirection will become the hallmark of post-quantum cryptography, and that it's not just about increasing the number of possibilities, but making it so that the possibilities are difficult or impossible to distinguish. Our final verdict is that the binary standard has been eclipsed by the power of matrix encryption. So is matrix encryption the most powerful cryptographic technology in the world? You decide. Join the decentralized cryptographic renaissance and go to https://matrixencryption.com to learn more and create a free account today. We have products available for download, with additional products soon to become available, together with tiered subscriptions and cryptocurrency and NFT integration on our roadmap.